this point where this peaks, it's the mean of our, you know, of this sum variable that you have. And there's another thing called the standard deviation. I think you already know all of this, right? Yeah, right. So that is just, you know, the Gaussian distribution that we have got there. So why does this happen? Like, why does this Gaussian distribution show up? Like, we were just rolling die, right? And we had a seemingly random sort of a variable, random variable. That's a nice thing. But yeah, why does this show up? And it's not just that this shows up with this particular distribution, you know, six-sided die roll. It will show up in any sort of case, really. Like, yeah, it will show up in all sorts of cases, basically. So why does this actually happen? And I'm going to show you a pretty mathy proof of this thing. So let's just start. So we are going to be proving the central limit theorem, the weak version of that, where you have the variables being identically distributed, independent variables, and it's not so okay. Yeah, basically identically distributed independent variables. Isn't that right? Yeah. Yeah, yeah, right. And we could in fact kind of remove the identically distributed part as well, but I guess it's okay to just use that. So let's just start. So yes, I do like to think about this summed up variable thing having a distribution given by the convolution, but this whole proof is not going introduce you to some background stuff necessary for this stuff. So first, the characteristic function in the so the characteristic function do is that you can write p of omega as this thing, because basically p of omega, you know the derivatives of p of omega, right? In fact, all the derivatives in terms of the moments. So you can write the characteristic function in terms of the moments, right? Cool. Now there's another important thing which is called the cumulant so forget about what a cumulant is, but basically this function is just natural log of the characteristic function. Now you might say, how do we calculate this thing, like natural log of this stuff? Well, I don't know. I really just don't know. It like kind of depends, right? Yeah. So basically you calculate it by some sort of a, you know, expansion, and then you like sum up a bunch of things, and so you get some series. You like evaluate the series and all that stuff, and that's how you get this natural log of p omega, basically. Now this natural log of p omega can also be Taylor expanded, obviously, and if we Taylor expand if we Taylor expand it to such that this sort of matches your p of omega, in that case, these coefficients that you have, x power n, the exponent value of that, well, they are obviously not going to match with whatever coefficients you have for natural log of p of omega. But these new coefficients that you have for natural log of p of omega, so the ones instead of the expected value of x power n, the nth moment basically, is given a new name. It's called the nth cumulant, right? So this small c over here, that represents a cumulant. So the nth cumulant is basically like this coefficient that occurs in the cumulant generating function. And yeah, that is in fact a definition of the cumulant. But anyway, so that's, for now we just think of it as some sort of coefficient, right? Like nothing too complicated about that. Now the thing is, these cumulants are related to the moments by a series of equations, right? So some equations which give us the cumulant using the moment. For example, the first cumulant, so the cumulant of x, that's just the moment of x, which is of course the mean. But then cumulant of x squared, that thing is actually cumulant of x squared minus the square of the cumulant of x, so the variance basically. And then the third cumulant gets like really complicated, and from that point onwards it's all like just really big, messy, complicated equations, which yeah, that's just the way it is. But in any case, let's just move on. All right, cool. So yeah, this is sort of the inverse of that, like moments using cumulants, but let's not go into all of that. Let's just go back to our proof, right? So now you understand characteristic function, cumulant generating function, what cumulants are, and now we can kind of finally get into this thing. Oh, first you need to know the multivariate Gaussian, obviously, right? So first we'll go for the multivariate Gaussian. So P of x vector for the multivariate Gaussian. Yes, this thing is just the normal Gaussian. I don't want that. Function. I think I have not written that anywhere. But anyway, so the multivariate Gaussian is, oh, okay, I have actually written that. It's given by this scary looking equation really, but it's sort of a generalization of the Gaussian distribution in single variable, right? So you just generalize that and you get this weird looking thing. Yeah, so it's just read it, basically you'll understand what's going on. So just like the normal distribution, so just think about it. If you had independent Gaussian variables in fact, and then you just took the joint distribution of that, then this formula would make sense suddenly, because then the covariance matrix would just be, so C is by the way the covariance matrix, that would just be a diagonal matrix, and then the determinant of that is like the product of the diagonal entries, and then C power minus 1, that's just like 1 upon sigma 1 square, 1 upon sigma 2 square, and so on in a diagonal matrix. And then this whole thing of x minus mu transpose C inverse x minus mu, that would just be x 1 minus mu 1 squared by sigma 1 squared, and so on. So this makes like sense suddenly, right? But of course in the more general case it doesn't make all that much of sense, but who cares? I mean, when I say sense, I mean intuitive sense, right? And yeah, maybe if I look around, I might just find some intuition on why it's the way it is, but I guess at this point we should just give it to the math and not care all that much. But yeah, so for a Gaussian distribution over n dimensional space is given by this formula, and this has the characteristic function. Yes, the characteristic function can also be defined for multiple variables. In fact, the Fourier transform for multiple variables is also defined, and you should look that up. It's not that hard, in fact. But the characteristic function is given by, once again, the Fourier transform of this P of x vector, and that happens to be this thing, x of minus iota omega vector transpose mu, which is basically the dot product between omega vector and mu vector. Mu vector is just the collection of means, by the way, of your variables x1, x2, so on, and minus half omega vector, the covariance matrix omega vector, basically, where the covariance matrix is defined like this, obviously. Yeah, so this is basically like just a second order cross, what is it called, second order cross cumulants, but then there are higher order cross cumulants which are like really complicated, but I won't actually go into that. So anyway, that's the covariance matrix, fine. And thus we have, so this thing is also called, so this is called covariance obviously. And then if you divide this thing by the standard deviation, all that stuff, then this is called the correlation and all. So it's kind of, it's useful at a lot of places. It's just good to know, right? And in any case, we can finally write a really good equation. So we can write, so we're taking the log on both sides on this equation. You can write this equation, and so you just get like natural log of p omega vector. That's this thing. Okay, cool. That's going to be useful later on. So that's for a Gaussian thing. Cool. All right. But what this kind of implies is that the higher cumulants are all 0. Okay, cool. So now let's get to the proof. Fine. So let's have this setting. You have multiple random variables which are identically distributed, and they are all independent. So IID variables called small x of I, and then you sum all of them up. That sum is a new variable capital X, right? You define this mu vector thing, which is just the collection of the means of these the xi variables, right? Yeah. So the mu vector thing is also like the mean of the joint probability distribution, right? So over the n-dimensional space, if that makes sense. And then similarly, the joint probability distribution has a covariance matrix, right? Then you can write the probability of capital X using this relation. So this is involving delta and all that stuff. But if you understand direct delta functions well, then this. So basically, this is an integral over n-dimensional space. In 3 dimensions. So p of x vector is, so p of x vector is, so that's of you being in that volume. I'm saying volume, but it's like n-dimensional volume times some function, right? Capital X is also, so the only times that you actually possible. So the probability of capital X, then you basically to the given capital X value, we just take that, and the taking part is done by the delta function. It's an n-dimensional right? So I should really just write this as delta n, but I guess we'll just move on. All right. What we want to do is kind of find the characteristic function of capital X, and so we do that by taking the expected value of e power minus I omega capital X, right? And we use the probability distribution of capital X to be integrating over the n. Right, so then what we do, we integrate using this d capital X thing first, right? And this delta function thing, well, we can really, this will just give us a 1. This will just like pick up, yeah. And so yeah, there's a bit of a hand weaving over there, but just take my word for it. And so what you'll basically get is over n dimensional space, the whole Rn thing, px vector e power minus I omega, this summation xi thing. So function high, right? Okay, and now notice that this little thing omega times summation of xi, that could be written as omega times 1 vector, that dotted with the x vector, right? So the collection of xi is the x vector. But notice that's exactly just the definition of the Fourier transform, right? So we're taking the and so just have the characteristic function evaluated at omega 1 vector, and so that's what this equation is basically, like px omega, that's just p of omega 1 vector. And so from here we can take a natural log and we can write the cumulative generating functions or a relation between them, and from there we can expand these, right, using that summation thing that I showed you earlier, and compare term by term. So when I say term by term, I mean like powers of omega, compare powers of omega basically, because this should be an identity in omega obviously. And comparing, what you get is that the nth cumulant for capital X, that just, this should not be the thing, we have already used n, sorry, so this should be, yeah, this is what should be the thing. So the nth cumulant in capital X is just n times the mth cumulant in small x, and that's kind of nice, isn't it? It's like really useful, because from that what you can do is that you can actually just write natural log of p sub x of omega. I mean, you actually have already written that in terms of but you can sort of approximate it and then write, and that will become useful. Okay, but we don't actually care about capital X all that much. What we care about is this variable small y, which is capital X minus n mu upon square root of n. Yes, this is the variable that we really care about. You want to find the probability distribution of this in the end. And just to remind, capital X is the summation of xi things, so we are doing summation xi minus n mu upon square root of n. There are reasons why we are doing this, so why we're defining it this way. The minus n mu makes a lot of sense. Basically, I'm just doing, I should actually probably say this is not minus n mu, but more like, yeah, whatever. We are in fact using the fact that we have, identically distributed variables, right? So I guess it's okay. So this minus n mu thing could be thought of as minus mu, minus mu, minus mu, and so on. So basically, we're just doing summation of xi minus mu I, right? And that upon square root of n, really, right? But that could also be thought of as the square root of the summation of the standard deviation of each variable. Sorry, the variance of each variable summed up, right? But then you have some sigma factor that you have to put in, but like, it's okay, it makes sense, right? That's what's important. Okay, and so now that we have defined this small y variable, we want to be writing the cumulants for y. So the cumulant for the first cumulant for y is just the expected value, which we know is just 0 at this point, because you are subtracting the you're subtracting the mean in the first place, right? The mean of capital X is in fact mu. Now the next cumulative is obviously the variance, and the variance turns out to be sigma square. Sigma is the variance, so sigma square is the variance of your xi, right, of any of the xi, but it's also now the variance of your y variable, right? Now what about the higher cumulants? So for them, what we can do is you can write you know, the mth cumulant as order n power 1 minus m by 2. So why is that the case? The n power 1 is from the numerator and the m by 2 thing is from the denominator. So you have the square root of n thing, right? You're going to take that m times because y power m obviously. But then x minus n mu power m, the cumulant of that thing. So x minus n mu can be expanded basically, right? What was I going to say? Yeah, I was going to say something. I kind of forgot what I was going to say. Oof. Yeah, I kind of don't remember. Okay. Yeah, right. Okay, so you have x minus n mu power m, right? And we just have to show that that thing, that expansion that you have, x power n minus n mu power m thing, the cumulative of that obviously, that is of, you know, order n. And it's easy to show that for, you know, the second cumulant, maybe even for the third cumulant, but eventually it gets hard and you have to do some sort of inductive thing and whatever. So I'm not going to do that. Just take my word on it that this is in fact order n. And so if it is the way I describe it, in that case, as your you know, n tends to infinity, this thing should just tend to 0, right? So this n power 1 minus m by 2 thing. And so what we have is that, well, yeah, that y power m, the cumulant of that is 0 in the limiting case as n tends to infinity. And in that limiting case, what you can do is that you can now write the so since the mean is 0 and the variance is sigma square and every other cumulative is 0, basically you just have sort of a standard, not exactly standard coefficient, that would be e power minus x square by 2, but you just have e power minus y square by 2 sigma square, right? That's yeah, with like the normalization factor as well. That's your distribution basically for y, and that is it. That's in fact the central limit theorem, the weak version obviously. And this even works, not this proof, but the central limit theorem, the strong version, that even works even when your you know, the variables are correlated, as long as they're not too so that too correlated part is like that might be sort of unclear to you, but basically is that as long as the cross correlations are you know, of order n power m by 2, right? So the mth cross cumulant is of order n power m by 2. Well, what will happen is that these will just kind of decline, and yes, that happens. The stronger version is like better obviously, and so it works in that case as well, even if they are sort of a little correlated. And so that's the central limit theorem. And the reason I'm making this video right now is because I have took this challenge of like making one video each day before 5 p.m. and I missed the deadline of 5 p.m. That's mainly because I was working on the project course. I had a meeting, so I just really didn't get time for anything actually. But hopefully this like redeems that delay. So okay, there's a lot of stuff which is like, I don't know, hard to understand for me as well, because I'm like just starting out on this stuff. But maybe tomorrow I'll actually kind of, you know, get deep into this and try to understand more, and that will certainly help me in the course. And this is like cool stuff. This is like what I came here for: probability distributions, you know, proper like statistical. I'm going to benefit from stuff. So I am going to tackle this head on tomorrow, obviously. So I'll see you guys in the next video. Bye.